The question is, what is a precise definition of a real number? The answer is, how much time have you got? It took more than 2,000 years to develop the precise definition of the real numbers, and we're going to review that today. Let's start with the natural or counting numbers, denoted by this pretty symbol n, and the set of counting numbers consists of the numbers 1, 2, 3, and so on forever. The first thing you notice is that we end up with an infinite set of numbers. They go on without end. When given a counting number, natural number, when you write c equals a times b, that means that a and b are factors of c. For example, 63 is 7 times 9. Notice that this last can be broken down even more. 63 is 7 times 3 times 3. When you get down to numbers that don't factor anymore, they're called primes. 3 and 7 are prime numbers. The smallest prime is 2, and 5 is another prime. So the first few primes are 2, 3, 5, 7, and then you jump to 11. 9 is not prime because it factors. One of the first questions asked about natural numbers is, are there infinitely many primes? The answer is yes, and the proof, which we won't go into, goes back to the ancient Greeks. It's reasonably elementary. There are, however, many important questions about prime numbers which are still unanswered. Even determining whether a large number is prime can be impossibly difficult, and this fact is in fact the basis of modern cryptography. One of the largest known primes today is 2 to the power 325826657 minus 1. This type of prime is called a Mersenne prime after the monk Mersenne, who during the 1600s pointed out that when p is a prime, then 2 to the power p minus 1 is very often prime. Prime twins are also an area of modern research. The pair of primes, 3, 5, are consecutive odd numbers, both of which are prime, and they're called a prime twin. The next such pair is 5, 7, and the next pair is 11, 13. The Twin Internet Prime Search and Prime Grid website has recently announced discovery of the largest known twin prime pair. They were discovered on January 15, 2007. And what you do is you take the following two numbers, 2003663613 times 2195000. Take that product, add 1, and subtract 1. And you get two consecutive odd numbers, both of which are prime, each of which contains 58,711 digits. In fact, just reading out the digits in the two factors in the product was rather lengthy. So you can see how hard it is to work with these things. The discoverer was Eric Vautier from France, and you can go to the website listed to get the whole story. If you'd like to make a lot of money, the Cray Mathematical Foundation has established a prize of $1 million US for a proof or disproof that there are infinitely many prime pairs. The natural numbers are great if you just want to count things. But if you're going to do accounting, you need integers, and that's basically why they were invented. If you lose money, you need negative numbers. And if you don't make any money at all, you need 0. So the integers are the numbers denoted by the pretty symbol Z that start with 0 and go both ways. On the right-hand side going 1, 2, 3, running through the natural numbers. On the left-hand side going -1, -2, and so on. Negatives of natural numbers. Now in this system, you can add, subtract, and multiply and stay in the system. But you cannot divide things into parts and stay in the system. 1/3 isn't there, nor is 2/9. So, finally, the rational numbers were invented. These numbers are ratios. Q is defined to be all ratios of the form P over Q, where Q is a natural number, and P is from the integers. The reason we restrict Q to be a natural number is because we don't want it to try dividing by 0. Now, to say that a rational number is a ratio is slightly incorrect. since 1/3 is the same as 2/6 is the same as 3/9. And you probably saw in school how if you take a stick and you break it into thirds and take one of those proportions, you get exactly the same piece as if you broke it into sixths and took two of those proportions. So in fact, a rational is a set of all equivalent ratios which reduce to the same result when brought down to lowest terms. However, you don't really need to keep this in mind. The relevant calculations are automatic. There are two other ways to represent rationals, one visual, one computational. For the rational number 1/3, as I said before, you can picture this number as 1/3 of a unit length. We can also do the long division to get a decimal expansion representing a rational. For example, 1/3 has the decimal expansion 0.333, and then the 3 is repeated infinitely often. So again, we have this notion of infinity coming in almost immediately when we start discussing numbers. There's a very simple theorem to describe the decimal expansion of a rational number. It says that the decimal expansion of a rational number will eventually fall into a pattern of the same block of numbers repeated forever. Notice that any finite decimal expansion that ends after a finite number of digits is automatically a rational number. For example, 13.67215558 is just the ratio 13672155578 divided by 1 with a whole bunch of zeros to put the decimal in the right place. Given any rational number, we can do the long division, and we're guaranteed that eventually we get a repeating pattern. For example, 11/17 is this horrendous decimal in front of you, but if you look at it, you'll see that it falls into a repeating pattern very quickly. Now, the pattern need not start immediately. For example, the number given on the screen there, x equals 0 point, etc. there, is a rational number. It finally falls into the repeating pattern 1, 2, 2, 1, repeated over and over, with a bunch of stuff at the beginning that isn't repeated. Can you figure out the numbers p and q for which x is p over q? Now, in some sense, rational numbers are the foundation of scientific and engineering computation. A computer can only do numerical computations with rational numbers since it uses finite decimal expansions, and we humans are just as limited. The ancient Greeks associated philosophical and religious importance to numbers, and they assumed for a long time that all numbers were rational, which suited their philosophy. Their beliefs are carried through to the present day in the standard belief that the number 7 is lucky and the number 13 is not. But the Greeks did discover that, for example, the square root of 2 cannot be expressed as a ratio of natural numbers. This is a very shocking discovery for them. For us, it's just a matter of saying, okay, there are more numbers than we thought. Let's have a look at this proof, which is very elementary and uses mostly common sense. We ask that you convince yourself of the following before we start. If you square an even natural number, you will always get an even number. And if you square an odd natural number, you will always get an odd number. Now let's suppose that the square root of 2 can be expressed as a fraction p over q, where, and this is very important, the fraction is in lowest possible terms. That is, p and q have no factors in common. Now let's manipulate a bit. Multiply through by that denominator q and get root 2 times q must equal p. Now square both sides and you write 2 times the square of q equals p squared. Now the product on the left, 2 times q squared, has a factor of 2, so it's an even number. Then the number on the right must also be even since they're equal. So p squared is even, but that means that p itself must have been even. So you can write p equals 2k for some natural number k. Start with the equality we had, 2q squared equals p squared. replace p by 2k and write 2q squared equals 4k squared. Divide both sides by 2, and you conclude that q squared is 2k squared. Now the product on the right side has a factor of 2, so it's clearly an even number. And therefore the left side, q squared, is also even, which means that q must have been even. Now think about it a minute. You've come to the conclusion that both p and q are even. That is, they each have a factor of 2. But we started out with the very reasonable assumption that we had eliminated all common factors from p and q. This is called a contradiction. Now you can either throw out the field of logic, or you can throw out the field of mathematics, or maybe we should admit that our initial assumption that root 2 can be written as p over q cannot hold. So for mathematics, as opposed to computation, we need to allow for a new class of number, the irrational numbers. We can again ask lots of interesting questions about these numbers and numbers in general. Are there infinitely many rationals? Sure, the integers are already rationals. Are there infinitely many irrationals? Using decimal expansions, the answer is easy to see. Just take a decimal expansion for any rational, say 1/3, which is 0.333. Now break that up in an irregular manner to create an irrational. And for example, insert a single 1 somewhere between two of the 3's. Then between the next two 3's, insert 2 1's. Between the next two 3's, insert 3 1's, and so on. So you get a number x that looks like this. This number has to be irrational because it never falls into a repeating pattern. Since you can do this infinitely many different ways from one rational, it seems like there are a lot of irrational numbers. In fact, George Cantor in the early 1900s showed how to count infinite sets, and he demonstrated that the set of irrational numbers is far larger than the set of rational numbers. Also, it's pretty easy to prove using decimal expansions again. Between any two rationals, there's an irrational. And between any two irrationals, there's a rational. So they're all mixed together in a way that's very hard to visualize intuitively. The number pi, which is 22/7 in the Bible, is in fact irrational, as is e to the power n for any natural number n, where e is Euler's number, the basis of the natural logarithms. These facts were proved by a French mathematician, Lambert, in 1761. It's important when reading about rational and irrational, and generally about numbers, on the web, that you be very careful. For example, the website encyclopediafarlex.com states that an irrational number multiplied by itself gives a rational number. This is patently false. For example, pi squared is irrational. Now our journey of discovery is more or less over. The real numbers, R, is the union of the rational and irrational numbers, and this suffices for mathematics. Now, the important thing about the real number system, and the fact that you've been using most of your life, is that we can do algebra with it. And we want to review those algebraic properties. R, in the modern language introduced by, among others, the great Aimé Noether, is a complete Archimedean ordered field. Now, please recall the words printed on the fabled Hitchhiker's Guide to the Galaxy. Don't panic. We're not going to use several of those words anywhere in our course, and we will explain each of them intuitively. For example, the initial word complete means intuitively that there are no holes in the real number line. In the language of physics, the real numbers are a continuum. Now, there are holes in the rationals. For example, if you lay out the rationals on a number line, like you did in school, at the location square root 2 and at the location pi, there are holes. There are no rationals there. Now to the word ordered. Well, that just means that given any two real numbers, one is the larger of the two. Archimedean, we will discuss if and when needed. Basically, it says there are no infinitely small positive numbers. The important word for us right now is field. The concept of field was developed by Emmy Noether, a German mathematician who died in 1935. She grew up in Germany, was the daughter of a very prominent mathematician, was not at all interested in mathematics until she went to university. She wrote some brilliant papers and a brilliant thesis, and so they tried to hire her at the University of Göttingen in the early 1900s, 1914, 1915. This was one of the greatest universities in the world. Quantum mechanics was being developed there, among other things, and the mathematics faculty was superb. However, because she was a woman, there was great resistance. One professor stood up and said he could not imagine German soldiers returning from the war, that would be the First World War, and being taught by a woman. The great mathematician David Hilbert stood up and said he could not understand why gender should be an issue in the hiring of staff for a university. After all, a university was not a bathhouse. And so the debate went. Well, 3 years after she first applied, she was appointed at the University of Göttingen, and she had a beginning of a great career there until the Nazis took over. Because she was part Jewish, she had to flee. Her brother fled to Russia, where eventually Stalin killed him as a suspect German. She fled to the United States, where she had a successful career at Bryn Mawr University. Now, what she and others working in modern algebra did was take all of the scattered facts and ideas that we use in computing with real numbers and extract from them the important ideas, and any collection of objects that satisfied their axioms, these ideas, is called a field. And here are the basic ideas. We have two operations, plus and dot, addition and multiplication we'll call them, and we can add and multiply and always get real numbers back. The system is closed under these two operations. The two operations are nice, even lovely. They are commutative, described by these two laws. They are associative, which tells us that we can group a sum of three objects, two at a time, any way we please, or a product of three objects, any way we please, and always get the same result at the end. Keep in mind that you can only add or multiply two numbers at a time, so this grouping property, this associative property, is really important. And then finally, we have the distributive law, which says that we can take a product right across a sum. In addition, we have three very important special elements. First of all is the additive identity, the real number which we denote by 0, such that a plus 0 gives you back a. In other words, it has no effect in addition. And the same thing for multiplication. There's a special real number 1 called the multiplicative identity, such that a times 1 equals a for any real number a. Then the very last axiom for a field is that there are inverses for both addition and multiplication. Now, these take care of what you may have noticed is the complete omission of discussion of subtraction and division. For any real number a, there's a number denoted minus a, such that a plus minus a gives you 0, called the additive inverse of a. For any non-zero real number b, there exists a number denoted b inverse, such that b times b inverse equals 1. And b inverse would be called the multiplicative inverse of b. Now, you're so accustomed to using these properties after 12 years of school, it's hard to take them seriously. But this short list of axioms, the field axioms, is the foundation for all of the computational and algebraic calculations you learned in school. For example, the binomial theorem that a plus b quantity squared is a squared plus 2ab plus b squared. Just write it out, look at it carefully, and identify the places where you used distributivity, associativity, and commutativity. They're all in there, and they're all absolutely necessary. You may have studied other fields in school without realizing it. The best example is so-called clock arithmetic, which is really just a study of finite fields, that is, fields with only a finite number of elements in them. If you use a clock with 5 hours on it rather than the usual 12-hour clock that we use, then the number 5 is also the 0 again, just like 12 on a normal clock is our 0. So we use the numbers on this clock, 0, 1, 2, 3, and 4. Using the clock, you get the following tables for multiplication and addition. It is a pain to verify, but these tables define a field. In fact, as long as we choose a prime number like 5, we get a field. These finite fields are very important in modern cryptography. To finish off this section, we'd like to go back to the integers and discuss some fairly simple but very sophisticated techniques for manipulating integers and finding out things about them. We're going to be working with small numbers mostly, but if you think about how big integers can get, like 58 digits, then you realize that these techniques are indispensable in modern computing. Now, the first notion is that of a divisor of an integer. And that just means that it's a factor. That is, that the integer n has d as a divisor if n can be factored as d times some other integer q. And when we list the factors, you have to take into account that we're working not with natural numbers, but with integers. So we have to allow for negative factors. For example, the number 8 can be written as 1 times 8. So both 1 and 8 are factors. It can also be written as minus 1 times minus 8. So there, both those numbers are factors. It can be written as 2 times 4. So 2 and 4 are factors. And so are minus 2 and minus 4, because it can be written as the product of those two numbers. So when we list the factors of 8, we have to start, if we start with the smallest, that is the most negative, we have to list the factors as minus 8, minus 4, minus 2, minus 1, 1, 2, 4, and 8. So using the integers rather than the natural numbers does lead to forcing us to be a little bit more careful, but it isn't hard to get used to. The next idea I'd like to introduce is that of a common divisor of two integers. Given two integers, m and n, d is a common divisor for those two integers if d is a factor of both. That is to say, m can be factored as d times some other integer, and n can be factored as d times some other integer. It's important to keep in mind we're working with integers, so we have to keep track of negative factors as well as positive ones. For example, if you want to list the common divisors of the pair of integers 6 and 9, it's quite natural to think of 1, which divides both 6 and 9, and 3, which divides both 6 and 9. But you also have to include minus 3 and minus 1, both of which are factors of 6 and 9. In the same way, if you're looking for the common divisors of 6 and 8, then right away you think of 1 and 2, but you also need to include minus 2 and minus 1. You can understand that common divisors are not easy to list in full detail by just taking a relatively simple example, 12 and 18. After a little bit of work, you come to the conclusion that 1, 2, 3, and 6 are all common divisors, but also their negatives are common divisors as well. Now, for a great many purposes in applications, it's the greatest common divisor of two numbers that matters. The largest of the common divisors of two numbers is called their greatest common divisor, GCD for short. For example, if you're dealing with the numbers 12 and 18, their greatest common divisor is easily seen to be 6. There's no larger number that divides both. For various reasons, the GCD is very important, but it's also very hard to find by brute force if you have a couple of very large numbers, say two numbers with 100 digits each. So we need an algorithm, a clever way of finding the greatest common divisor of two numbers. This is called Euclid's algorithm because it does go back to the Greeks, and it's very simple. There is a proof in the notes. We won't go into the proof here, but instead just outline how to use the algorithm for finding a GCD. Basically, we do a set of divisions. Let's assume for simplicity that both m and n are positive. That is, they are natural numbers. And let's assume that m is the smaller of the two. So we can divide m into n and get a quotient and a remainder. It's that remainder that matters. Now, if you look at the equation, n over m equals q1 plus r1 over m, that's just describing the long division process. The quotient is not of interest to us. The remainder is what matters. We again do a long division. Now notice that we started out with the two numbers, putting the smaller one on the bottom. The next division involves two numbers using the smaller of the two integers, m, divided by the remainder we got in the first step. And of course, we get a quotient, q2, plus a remainder, r2. And now we continue this way using our previous divisor, r1, divided by our previous remainder, r2. And we get a remainder, r3. And in the next step, we divide r2 by r3. And we keep going until we get a remainder of 0. And the very last non-zero remainder we got is the GCD. It's a beautiful algorithm, very simple. And the proof is quite transparent, as you see when you read the notes. Let's look at how the algorithm works with an example. Let's find the GCD of 55 and 132. So we divide 132 by 55, and we get a quotient of 2 and a remainder of 22. So we divide 55 by 22, and we get a quotient of 2 again, and a remainder of 11. And then we divide 22 by 11, and we get a remainder of 0. Our last remainder, non-zero remainder, 11, is the GCD of those two numbers, 55 and 132, guaranteed by Euclid. It's just that simple, and it always works. The reason we're interested in the greatest common denominator is because it's a very useful tool in finding other numbers that are more important. For example, if you're trying to put together a couple of fractions, for example, 3 over 20 plus 1 over 28, then you need the common denominator, as it's called, which in this case, as you can check with a little bit of work, is 140. How do you get 140? Well, 140 is the least common multiple of 20 and 28. What's the least common multiple? It's the smallest number that has each of the given numbers as a factor. 140 does have 20 and does have 28 as factors, and it is the smallest such number. It's called the least common multiple of those two numbers, and it is the common denominator when they are denominators in a fraction. The least common multiple of 3 and 6 is 6. It's the smallest number that has both 3 and 6 as factors. The least common multiple of 9 and 12 is 36. That's the smallest number that has both 9 and 12 as factors. Now there's a very simple connection between the least common multiple of two numbers, m and n, and their GCD. Namely, you take the product of m and n, take its absolute value, that is, erase the minus sign, and divide that product, m times n, by the GCD. And that will always give you the least common multiple. If you think about it, the reason is simple. When you take the product m and n, you're taking all the prime factors of those numbers and multiplying them together. So you're repeating all the prime factors they have in common twice. When you divide by the GCD, you're striking out one copy of each prime factor that's repeated and getting all the prime factors between the two that are not repeated, and that's the smallest possible number that has both m and n as factors. Let's look, for example, at finding the least common multiple of 20 and 28, so we can put together this fraction that we described at the beginning. Well, you divide 28 by 20, and you get a remainder of 8. You divide 20 by 8, you get a remainder of 4. And 8 over 4 has a remainder of 0, so the GCD is the last non-zero remainder, which was 4. Then, our little formula for computing the least common multiple of 20 and 28 says we take the product, 20 times 28, and we divide by the GCD 4. Lo and behold, that number is 140. Now you can understand that this is a very powerful way to find the least common multiple if you have to put together a pair of fractions with huge denominators. And of course, all this is written into modern computer programs to enable us to carry these things out on the computer.